That is my middle dog scratching on the carpet. I don't know what she's scratching about. Scratches in the same spot for the last 2 years. Okay, so I want to pick up from Monday right here. So, let's simplify this. Okay, so these are very common monosaccharides. I don't know if you've heard of galactose before. If you've taken anatomy physiology, you probably have heard of galactose in terms of the nervous system. Um, okay, so galactose is one of the amino acids, not amino acids, monosaccharides you're going to need to know. They're going to be uh, three of them. There's glucose, galactose, and fructose. We're going to be going through those during this lecture today. Okay, another thing I want you to pay attention to is the anomeric carbon is always on the right side, and the anomeric carbon allows this hydroxyl group to be up or down. Also note, this is going to be up or down. If it's up, it's going to be beta. Down, it's going to be alpha. Okay, the chemistry is the same, whether it's alpha or beta, until they link up with another monosaccharide. And you'll see that along the way here. Then it's going to be crucial as to whether it's alpha or beta, because if one needs to be done and the other, it won't work. So that's why we distinguish whether it's an alpha or beta. If you're just looking at a monosaccharide by itself, you can either write it as an alpha or beta, as long as you name it correctly. Also, remember, you don't need to add the D. You may add the D, and there are no natural L saccharides in our body. We always have the D form. So I don't even go into the L form at all, other than in the beginning of yesterday's presentation, we talked about how those distinguish between the D and the L. But other than that, we're doing Ds. When we get to amino acids, those are going to be the Ls. And remember the chiral carbons from Monday. If you have a chiral carbon, then you can have a D or L formation. Okay, so let's go on here. This is ribose. I'm sure you've heard of it in terms of RNA. DNA, this is what's missing. This is the deoxy part. This goes away for deoxyribose. Okay. Oh, and this is the anomeric carbon here. And the anomeric carbon again is where the hydroxyl group can be in the beta or the alpha configuration. All right, now this is crucial understanding this. The cyclic form of the monosaccharides is the most stable, hence it's the one that's usually shown. But there is a small percentage when these guys open up. And when they open up, it looks like this. So if we redraw these over here, I'm going to do glucose now. And I'm going to do a beta glucose. And this is the anomeric carbon. And this goes 1, 2, 3, 4, 5, 6. So, looking at the glucose now, because it's a hemiacetal, it can revert back to its original aldehyde and alcohol. So how do we know it's a hemiacetal? Okay, we go through our 3 steps. We have OCO, and we have an OCO, so that's a yes. Do we have hydrogen present? And there is a hydrogen here, so yes. And what about OH present? Yes. So this means it's a acetal or hemi. This means it's a hemi ketal or hemi acetal. So that's the hemiacetal. Very important, very important. And I'm really stressing this because a lot of the chemistry is determined by the fact that a hemiacetal exists or does not exist. Now, as you remember from acetals and hemiacetals, it can back up or it can go forward. Okay, if we back up a hemiacetal, it goes back to the aldehyde and alcohol that created it. Okay, so this is going to be the alcohol oxygen. And that's going to be the aldehyde oxygen. Okay, so what does that look like when it opens up? Okay, we're going to make this into an alcohol and this into an aldehyde. There's the alcohol. And here's the aldehyde. Now, once this opens up, we can have all the aldehyde reactions. We can have all the alcohol reactions as well. And again, this is the more stable form, the closed one. So this is more stable. That's why outside of a chemistry class, you won't see the open form of the monosaccharides or disaccharides or polysaccharides or oligosaccharides. They're always closed because that's the most stable form of it. Okay, so this is another really important now, star time. And once it's opened up, then it can fall back into a alpha or beta form. Okay, and again, the anomeric carbon is where the alpha beta designation comes from, where the hydroxyl group can go up or the hydroxyl group can go down. Now, this is with a six-membered monosaccharide. There are also five-membered monosaccharides. Okay, the six-membered, oops, let's see here. Why is this moving around? The six-membered ring is called a pyranose. The five-membered ring is called a furanose. We always draw the anomeric carbon to the right, just an international thing. The technical name for the alpha beta versions of each of these is called anonomers, coming from anomeric. And it has to do with whether the OH group is hanging or going up. Okay, so this is an example of a furanose, fructose. Furanose comes from the name of fructose, by the way. Okay, so it is also going to be seen 99% of the time is in its cyclic form, its most stable form, but it does open up. It opens up to a ketone right here. So now, numbering of furanoses, or in this case, fructose, this is carbon number 1. So in furanoses, carbon number 2 is the anomeric carbon. Now, real quickly, the formula for this is C6H12O6. Same formula as glucose. That's why in a lot of nutritional magazines, they'll say, well, it's a sugar, C6H12O6. It's not the same sugar at all. It is a isomer of glucose. And unfortunately for our bodies, it can come into the, excuse me, it can come into the metabolic pathway where we metabolize glucose into ATP. The first major part of that metabolism is called glycolysis. Fructose comes in at the third step of the glycolysis part. So it's utilized just like glucose in the body. However, there's a big difference is it's not regulated like glucose is. So it tends to go off the rails. Okay, so this thing opens up just like glucose and galactose, all the other. Okay, so now this can also be alpha or beta. In this case, this is the alpha fructose. Okay, and then once it opens up, it can go fall back down to the more stable state of alpha or beta fructose. Now, in a minute, I'm going to talk about the reactions of these guys. Fructose, Let's see, let me go over here. Okay, we talked about aldehydes and ketones. We had one of the tests was the Benedict's test, and that was involved with copper +2 being reduced to copper +1. When that happens, the aldehyde gets oxidized to the acid. Ketone does not get oxidized to the acid. So if this fructose opens up to a ketone, we should get a negative Benedict's test, but we don't. We get a positive Benedict test because when the fructose opens up, it does a little sneaky trick and turns into an aldehyde momentarily, in which case it'll give a positive Benedict's test. And it goes through something called an enol. And you do not have to know this. I'm just saying why a ketose like fructose can give a positive Benedict's test. Okay. So fructose is the exception when we're testing for sugars. And this is where we get the concept of reducing sugar. Will it give a positive Benedict's test? So what the reducing part is talking about is reducing copper +2 to copper +1, or in the case of Tollens, silver +1 to silver metal. Okay, so that's going to be definitely a question on the test. For a lot of, when we go over the practice test, I'll show you how that comes out. You may have a disaccharide there, a monosaccharide. I'll ask you, is this a reducing sugar? Yes or no? Why? And the deal is you look for a hemiketal or hemiacetal. Those open up to an aldehyde. Aldehydes will give a positive Benedict's, positive Tollens test. So if we, as a review, go back up to glucose, there's the aldehyde. Hence the positive Benedict's test. For fructose, it opens up to a ketone, but the ketone can turn into an aldehyde, making this carbon number 1 an aldehyde, which gives a positive test. Okay. So we always draw the anomeric carbon, the one where the OH group can open up on the right. Okay, so all right, so we have Benedict's solution on the left here, and it's blue because of the copper copper ion. And we have glucose, a really weak solution of glucose, and a really strong solution of glucose. So this is a weak, strong. Okay, and then when we dump this into there, because it's glucose, glucose being hemiacetal can open up to an aldehyde, it ends up reducing the copper to copper +1. And the orange color is cuprous oxide. So this is cuprous oxide. And it's a very fast reaction also. When we do the carbohydrate lab, um, you'll see it's quite a fast reaction. Some of them are much slower. So the question is it reducing sugar? Boom. And the reducing name in the name reducing sugar comes from the classic test. Usually we use Benedict solution because it's so fast. Silver is expensive to buy, so we usually use, and it's also much slower reaction. So we use copper instead of the Tollens test. Okay, so we haven't talked about esters yet, but the OH on glucose can act with an acid and produce something called a ester. And that's what these are. We're going to talk about these in depth when we get to Unit 3 on esters. So until Unit 3, don't worry about this slide. Okay. Now, this next part, we're going to get into what happens when we have a sugar, which is not a sugar, a monosaccharide like glucose, and which is a hemiacetal in its cyclic form, reacts with an alcohol. So we're going to throw in a 1-carbon alcohol, and then that's going to go over to this guy. Now, this is a hemiacetal. This is a full acetal. Now, the full acetal does not have an OH on it. That would make it a hemi, like over here. So this is, let me write this bigger. Okay, it's a hemiacetal because of the OH. There's no OH over here, hence it's a full acetal. So this guy will give a positive negative Benedict's test. So this guy is reducing sugar. Not a reducing sugar because there's no hemiacetal present. Now, whenever we form an acetal, whenever a monosaccharide reacts, we form a glycosylic linkage. Okay, and the reason why and the resulting molecule you create is called a glycosides. Now, these are really important reactions because if anyone is diabetic, they're watching their something called A1C. And A1C actually is a glycoside formation, where what happens is the sugar, glucose, will react with some molecules on the outside of a red blood cell and stick there. And what happens, the A1C test checks on how many of those glucoses are stuck on your red blood cells. And it's a metric to determine whether your blood sugar has been maintained over. And this is a long-term deal. Short term, you look at your blood sugar by pricking your finger, checking your sugar at that moment in time. And A1C does it over a period of months. But anyway, it's a very common reaction. Okay, so I mentioned this earlier. This is ribose. We've got these two hydroxyl groups on carbons 2 and 3, and then the deoxy version loses carbon number 2's hydroxyl group. Okay, so let's go through these in detail. Glucose, again, you're going to need to, and you can do this doing the CH2OH, or you can just come up and go like that as well. I usually do it with the latter, with the line draw. Okay, this is the most biochemically important monosaccharide. It's used everywhere in your body. It's used so much that if it's not glucose, it'll be turned into glucose before you can use it. For example, fat metabolism. When you burn fat, it has to be first converted to glucose before it can be burned. Okay, as drawn, this is the beta one, and then of course, coming down, we have the alpha version. It's one or the other. Okay. Galactose. Now, if you know the structure of glucose, you know the structure of galactose, all you need to do is flip this. Instead of going down, carbon number 4 here, it goes up. Everything else is the same. It's got a hemiacetal, this guy here. So this is a reducing sugar. Now, fructose is a furanose, meaning it's a 5-membered ring. And the way I remember to draw it is the opposite of glucose. So if the OH group here will go down with glucose, fructose is the opposite. So instead of going down, up, down, this goes up, down, up. That's the way I remember it. Okay, it is a ketohexose, 6-membered or 6-carbon. As I mentioned before, it's the same formula as glucose and galactose, C6H12O6, and it's much much sweeter than either glucose or galactose. Okay, excuse me. So let's talk about now when we hook up 2 monosaccharides together. Okay, when we hook up 2 monosaccharides together, we get a disaccharide. And the important part on disaccharides is what are the sugars, monosaccharides involved, and what's its linkage? And lastly, is there a hemiacetal present? Because we're going to talk about some disaccharides where hemiacetals are present and not present. So remember, if a hemiacetal is present, it's a reducing sugar. If it's not present, it's not a reducing sugar. Okay. So the essence of this reaction has to do with the hemiacetal and an alcohol. In this case, it's the alcohol on another glucose for this particular disaccharide. And it's on carbon number 4 or carbon number 6. When we look at glycogen, for example, it's attaching to the carbon number 6 and the carbon number 4. But most of the time it attaches to carbon 4 because it's the most clear hindrance-wise OH. In other words, it's out in the open the most. So there's less interference with carbon number 4. That's not to say that it can link up with carbon number 3 or carbon number 6 or carbon number 2. Because those all exist biochemically. But this is the one, it's the most prominent. It's hooking up to carbon number 4. Okay, so we have a hemiacetal plus an alcohol. That means we're going to form a acetal. And one other little thing here is there's a there's a hemiacetal because they're both glucoses. So the second glucose also is a hemiacetal. Okay, so what happens is, and that's going to come into play, the second hemiacetal, in a minute here. Okay, what happens is these link up, and this is a let's see, if we analyze this linkage, okay, so we're looking at OCO. So let's do our analysis. Okay. So we have OCO. We have H. No, there's no H there. Now, which is wrong, by the way, because if we look at this, remember, carbon's got 4 bonds. This carbon here, the anomeric carbon, has got 1, 2, 3 bonds showing. So that means there's an H there. So this is going to be a Y. And then, is there a hydroxyl group there? No. That means this is an acetal. Now we also have another OCO over here. This guy here. So OCO H is a yes, and OH is a yes. Oops, yeah. So that's what makes this a hemiacetal. So maltose, discovered in beer, hence the name maltose, is both a full acetal and a hemiacetal. So this is a reducing sugar because of the hemi. Okay. Now, whenever we have a linkage between two monosaccharides, there is a linkage. And that linkage can be a couple different things. Depends on where it connects and whether the anomeric hydroxyl group to start with is up or down. In this case, we started with the alpha glucose, and we linked up to carbon number 4. So when we write that linkage, we're going to write it as alpha 1, 4. So this is the This is the anomeric hydroxyl group going up or down. And this is the C4 alcohol that we linked up to on the adjacent monosaccharide. So it's an alpha 1,4 glycosylic linkage. If it was a beta 1,4 glycosylic linkage, it would not be maltose. It would be something else. Now, this is a typical test question. I'll give you a disaccharide and I'll ask you a whole bunch of questions. One, name it. Number two, is this a reducing sugar and why? Okay, does hemiacetal exist in that? Yes, right over here and highlight it. Number two, what's the linkage? Name the linkage. Those are typical questions I would ask you on a test for disaccharide. And this is one of the disaccharides you need to know, maltose. There are three of these. Now, the reason why it's a reducing sugar because we have a hemiacetal here that opens up to an aldehyde. Oh. The next one is lactose. Lactose is galactose plus glucose. So this is the on the left is a galactose. Notice the OH group is going up here, not down like glucose. And I don't know why. This is old notes. Okay. All right. So let's analyze this. Okay. First of all, when galactose and glucose come together, we form a linkage. And that linkage is right here. And another thing to note here is we have a hemiacetal there. That means automatically it is a reducing sugar. But look at the linkage here compared to that linkage. That's a V shape, meaning alpha. And this is kind of like going up beta, because this starts with a beta hydrogen OH group here on the left. So now the linkage is going to be, beta 1,4. We're attaching to the C4 carbon on the glucose, and we're starting on the anomeric carbon number 1 in the beta configuration. So lactose has to have a galactose in the acetal formation attaching to a glucose molecule with a beta 1,4 linkage. Beta 1,4 linkage. Only if it's not a beta, if it's an alpha 1,4 linkage, it's not lactose. If you don't start with galactose, it isn't lactose, etc. So these are very, very specific. And again, the reason why it's so specific has to do with enzymatic action on these molecules, because the enzymes active sites are specifically designed to only accept certain glycosylic linkages, period. Okay. So, so lactose is a beta 1,4 linkage. It's a reducing sugar because of the hemiacetal. And the third disaccharide you need to know is sucrose. Now, sucrose looks really different really different. Okay. Sucrose has got a glucose and a fructose monosaccharide linked together here. Okay, so that linkage is different. This is a alpha 1 beta 2. Okay, so first of all, are there any hemiacetals present? Well, here's an OCO, no hydroxyl group, so that's not a hemi. Here we have OCO, OCO, and no hydroxyl group there either. And there isn't, oops, excuse me.
Professor, we can't see the notes you drawn.
What's gone?
We can't see the notes that you're jotting down.
Okay, so let me back up then. Let's look at the way this is set up. Okay. We start with glucose linked to a fructose. And this is the linkage here. We have OCO and OCO. Oops. Okay, so we have two deals to analyze. Is either one of them a hemiacetal? Okay, so analyzing this, we have on the top here, we have let's get rid of this here. Okay, so we've got an OCO. We have an H, yes. And we have no OH. Okay, so that means I'm talking about this guy here. This would be the yellow one. Okay, so this means it is a full-blown acetal. Okay, since there's no OH, it can be a hemi. And because an H is present, it's an acetal. Okay, now let's do the purple one. Okay, so we have an OCO. We have no hydrogen. And we have no OH. Okay, so that makes this a ketal, not a hemi. So a reducing sugar requires a hemiacetal. There is no hemiacetal here. So this is not a reducing sugar. Okay, now let's look at the linkage. So whenever we hook up two monosaccharides, there's always a linkage, glycosylic linkage. Okay, here we have the original glucose, the OH is going down, so that's an alpha. And it comes off of carbon number 1. And down here, it's going up, so that's a beta, and it's attaching to carbon number 2. Hence, it's a alpha 1, beta 2 glycosylic linkage. Right here it says reducing sugar. Why isn't it reducing sugar? No hemiacetal. No hemiacetal. Boom. It's either yes or no. Nothing in between. Okay, so that's the third disaccharide you need to know. Now, frequently, when you read about sucrose, you see it written more horizontally than vertical like this. It's more correct to write it vertically than horizontal because most books don't care about the linkage. Because this is an organic chemistry class, we do care about linkage, hence we have to write it vertically like this. Okay. Now what I want to do is stop here. You're going to need to know two oligosaccharides, raffinose and saccharose. And some different kinds of polysaccharides. These are very common oligosaccharides. And then we're going to get into polysaccharides. So I want to do that on Monday. Okay, so I'm going to back up here. So we're going to stop here for today. Okay, I want to do one more Benedict's reaction though. Let's take maltose and run a Benedict's test on it. What does that look like? Okay, so what I'm going to do is I'm going to draw maltose, excuse me, the in its closed form, because remember maltose, the glucose on the right with maltose. Let me just show you that maltose again real quickly. This is maltose. So it's got two glucoses. The one on the right is a hemiacetal. The one connecting the two is a full acetal. Okay, so hemis open up, fulls do not. Let's go back up to where's the disaccharide start? Here it is. Okay. So we're going to take maltose. The Benedict's test. Okay, so we start with maltose. So we need Okay, so this is going to be alpha maltose. And the reason why it's alpha is because this is going down. Okay, that's a hemiacetal. We've already established that. So that means that can open up. The aldehyde. Okay, so now we have an aldehyde. And now we're going to throw in copper. Benedict solution uses copper plus 2 in a basic environment. So what's going to happen is okay, so we have copper plus 2. So the copper plus 2 gets reduced, and the aldehyde gets oxidized. Now, the reason why this is a minus over here is because it's in a basic environment. So that's the Benedict's test, and this is what turns out to be orange color, this here, which ends up being cuprous oxide. And this happens very fast. Okay, so that's a pretty complicated reaction, and because it's structures, but really, the only thing going on is we have an aldehyde right here. Aldehyde being oxidized to the acid, just like unit 1 and unit 2. That's all it is. All this other stuff is just, that's the problem with carbohydrates. You have simple reactions, but the structures are complicated. But the essence of the functional groups, what's going on there is very straightforward. I know, easy for me to say. Okay, are there any questions about the Benedict's reaction? You really need to know this reaction. And for this test, you can have 2 3x5 no carbs, just because of the complexity of the carbs. Okay, so are there any questions about any of these reactions or structures? Now, it's really important to keep up with lectures on this unit 2, is because the structures get more and more complicated. Because the reason I stopped where I was is when we get into the illegal saccharides, like raffinose, we've got, instead of a disaccharide, in this case, it's a trisaccharide, which is the smallest oligosaccharide. But we've got lactose, glucose, and fructose all together. And notice where the bonding is taking place on carbon number 6 rather than carbon number 4. and then we tie into sucrose. So raffinose is a fancy sucrose. And this is not maltose on a noise. So anyway, that's why I wanted to leave that till Monday. Okay, how are we doing? All right, we've taken in a lot of information. So that's why I'm ending this now. Um, okay, so then I'm checking chats. I think we're up to date on the chats. Yes. Okay, what do you guys think? And just FYI, because of the structures, not the reactions, but because of the structures, most people feel Unit 2 test is more complex. But don't forget, I give you everyone extra time. And you can have 2 3x5 note cards. Okay, you guys are awfully quiet.
I have a question.
Sure.
So for the test, 3x5.